Okay, good afternoon, everyone. So we are talking about chiral spin liquids at the end of last lecture, and I want to continue that discussion and finally show you our long-awaited example of Chern-Simons topological phase described by Chern-Simons gauge theory, where we actually emerging from some microscopic Hamiltonian of electrons on a lattice. Okay, but before I start, any questions? Also, I should note the last problem set is on the website, and I made some corrections to it today and I added a few more hints. I'm a little worried I'm overburdening you with this last problem set and also preparing for your presentation. So, well, let me know if that's the case. And also, like I urged in my message on Slack, look at the problem set soon, and I'm sure Hayu and Darshan will be happy to take you along, a fair bit of the way towards the solution of any problems you get stuck in. I mean, I think they're all relevant problems. Will give you a better understanding of all of this if you go through them. All right, any comments or questions?
Subir,
okay.
Can I ask a
yes,
question?
Go ahead.
Yeah.
Yes, please.
So in the classification we talked about last time with these different Schwinger bosons and fermions, I was a little confused why we start with the same microscopic Hamiltonian, but we just rewrite it in terms of different variables, which are supposed to be equivalent representations, right?
Yes,
but in the end, we get different phases. Is it because we're just looking for different saddles, or are we changing the microscopic Hamiltonian?
No, well, we don't, as you can see from the way we proceed, we just guess some effective Hamiltonian for the partons. We don't actually work it out. But in principle, if you really worked hard enough, you should be able to start from either this representation or that representation and end up with the same answer. Now, what happens is that sometimes there are certain states, like the chiral spin liquid state, where that answer emerges very nicely from a very simple mean field theory of these partons. But to get it from the other partons requires a much more complicated procedure where you can't treat them as just free particles, basically, was what happens. So basically you try to use different representations because they give you rather different saddle points. That is, their mean field theories at the mean field level are rather different. But if you treated it more exactly, you should be able to get it from either side. Now, there's one exception to this case where we can get the same answer from either approach. And that's the case of the Z2 spin liquid. We can start from the bosons S and just pair them up and then get the gap state, and you get a Z2 spin liquid, which is what we did on the triangle lattice. And then the S boson itself becomes the E particle of the Z2 spin liquid. Conversely, you could have addressed exactly the same Hamiltonian using the F particle, and then the F particle becomes the epsilon particle of the Z2 spin liquid. Now, which is the better approach? Even though at least topologically they're in the same state? Well, again, that depends on numbers. Depends on the specific Hamiltonian, in which case is the S particle lower in energy, in which case is the E particle lower in energy, in which case is the epsilon particle lower in energy. That's an invariant statement, which you can't predict ahead of time without doing some very careful calculations. And then towards the end of the course, we're going to see that the same trick will help us understand even these gapless CFTs. For the gapless CFTs, there are dualities that emerge at long distances, and those dualities help us see the equivalence between the bosonic partons and the fermionic partons. Okay.
I see. Thanks.
Yeah. But really, we just, you know, we're just trying whatever works. I mean, that's the honest answer. And because we do some very simple mean field treatments and then hope to get some understanding of the topological phases. Um, and I think the remarkable thing is that as essentially all known topological phases, certainly those that have anything to do with any experiment, uh, can be described by some kind of very fairly simple mean field theory on some parton construction, which is why I'm using it. It seems to work in practice. Uh, so it just becomes a matter of finding the right parton construction to describe a particular state at a mean field level. And that's really what all I'm doing in this course. So for the chiral spin liquid, in fact, it was originally written down as a theory of bosons by Laughlin and Kallmeier, of bosonic partons. Uh, but actually, no, they did it another very clever way. But the simplest way to get it, which is the way Wen, Milchik, and Z got it, is by using fermionic partons in a band of a Churn number. So what we do is we take this fermionic parton construction, you put it into your favorite antiferromagnetic Hamiltonian, and then after some rearrangement, you get a term like this, a 4 Fermi term, an interaction term from the exchange interaction Jij. Then you do a mean field theory on it by Hubbard-Solonovitch transformation by introducing this field Q. Notice now it's F dagger F rather than S dagger S dagger as we had before. And then you just replace Q by an average value. So when you do that, you get some some free fermion Hamiltonian. There's also a on-site term that imposes the constraint. And it turns out here that there's a very simple solution of the constraint that this is just zero. By particle hole symmetry, you want to be at half filling, and so the chemical potential is just zero. So now we just focus on this Hamiltonian, and people's work has shown us, where did it go? Right here, that these are the values of Qij that seem to do well on the class of models that give you this chiral spin liquid. So this is really at this point, a very crude guess, but it's a guess that allows us to build new types of states. That's kind of what we're trying to do. So this configuration has the feature that if I compute the flux, which is the product of the phases of the Tij around any triangle, I get pi over 2. So for example, if I go anti-clockwise, let's go clockwise this way, clockwise around this triangle. Then here is +1, here is -I because I'm going against the arrow, and here is -1. So that gives me an I. Clockwise around this triangle gives me an I. How about clockwise around this triangle? I get an I. Clockwise around, this one here. So you would go clockwise. When I'm going clockwise, that's anti-clockwise. This is clockwise. You get an I and a plus and a plus. And then the fourth one, which is the fourth one? Anyway, pick any triangle, any right triangle like this. There's 4 in each square, and all of them clockwise give you an R pi over 2 phase. So basically, this is like a Hofstadter problem where there's a flux of uniform flux of pi over 2 in every right triangle, small right triangle. So that makes it very likely that you're going to get bands with Churn number. And indeed, that's what you find if you diagonalize this Hamiltonian. This is what it looks like in momentum space. And you just work out the band structure of that. You get this band structure here. So this is the upper band, and there's another band which is just the mirror image of this at negative energies, and you occupy the mirror image band. So what you notice here is that, at least for the parameters chosen, there are these minima here, and near the minimum, the dispersion you can work out looks like the dispersion of a relativistic Dirac particle. So you can think of these minima as representing, some emergent low energy Dirac particles, at least near the minima. And how many Dirac particles do I have? Well, you can see two of them, one here and one there. And then there's spin up and spin down. So there's a total of four 2 plus 1 dimensional massive Dirac fermions. And the mass has to do with the fact that this doesn't go exactly to zero. It's a parabolic minimum at the min. Furthermore, you can even actually take this matrix, the Hamiltonian is this matrix, this 2 by 2 matrix, and take the continuum limit appropriately near those points, just like you do with graphene. And after some, this is what you get. And then after some changes of notation, which are all described here, that should be an F over there. Let me change that. So this is an F. Then you get, in fact, precisely the massive Dirac Hamiltonian. So you can actually derive the relativistic form with all the notations that particle physicists love for this minimum and the other minimum and so on. Okay. All right, so that's great. And then from this Dirac dispersion, you can work out the Churn number. So that's easy to do in this limit, and I think how you probably did that in one of the sections. And basically, for every Dirac particle m, you get a Churn number of a half for any given band. So they have to be an even number of Dirac particles, otherwise you get half integers of Churn number, which you know is not correct. So you get a Churn number of a half, and the key question is it plus half or a minus half? And that depends really on the details of all these plus minuses here. And if we just work out those signs, you get either +1 or -1. And that's the quickest way, without doing the full band structure, of figuring out the Churn number of any band. Just hope that it has some almost Dirac points and just compute these signs near the Dirac points, this sign there and that sign there, and the sign of the mass. And together that you can quickly figure out what the Churn number is from that. So anyway, so you do all of that and you find that the upper band has Churn number +1, say, and the bottom band has Churn number -1. All right, so that's the mean field theory. You get spin-ons moving in a Churn band. So this turns out to have remarkable consequences to the gauge theory, because now let's take the mean field theory and do fluctuations. So in the mean field theory, you just set the Qij to some fixed value. Now we're going to fluctuate them. We're going to go, we found a saddle point, now we look at fluctuations about the saddle point. So what's the important fluctuation of Qij? Well, just like they were for the Schwinger boson theory, they are the phases of the Qij. Those are the only ones that can possibly give you anything interesting, because they're constrained by gauge invariance. Okay, so what is the gauge invariance of the theory? Well, this is an exact statement of the underlying path integral, which we've met before. There's a gauge transformation, rho I of tau, where rho is the arbitrary function of I and arbitrary function of tau. And if you make this change a variable, you will get the same action back. So there's a gauge invariance, and this tells us that the phase of Q transforms this way as a function of rho I. And now you see that this is actually a very nice form. It's just the difference. So if you imagine that the phase is slowly varying, and we're only interested in things that are slowly varying on the scale of the lattice, then this, so J is equal to I plus X, let's say, just one distance away. And this quantity here is just equal to I, which is the number I, times d by dx of rho. So we see that the phase of Q changes by the gradient of the gauge transformation. And that immediately tells us that the phase of Q is just like a gauge field. So we just call the phase of Q the gauge field little a, and A will transform just like any self-respecting U1 gauge field. So there it is. So now there's our emergent gauge field, the phase of Q. And this is actually the ease of the fermion way of doing things. As long as you don't have pairing, the phase of Q is automatically just your U1 gauge field. So just knowing this, now when we do fluctuations, we can, without any work, we can figure out what is the correction to the Lagrangian for the spin-ons, this Dirac Lagrangian. They're going to couple to the gauge field, and how are they going to couple? Well, they're going to couple in the only way it's possible, because from gauge invariance, and all you have to do is make that gradient a covariant gradient. So extremely simple. You just work out the theory of the spin-ons, and then you gauge everything, and you have an emergent gauge field, which is strongly fluctuating. Okay, so there's our theory now. Our theory really is quantum electrodynamics coupled to 4 species of massive Dirac fermion. That at least at low energies, that's the complete theory of fluctuations about this state. Okay, so now what's unusual about this theory? What's unusual about this theory, of course, is the Churn number of the fermions, which is partly hidden in this notation, because in this notation, you've made kind of different choices for the continuum fermions at the different values. So you really have to go back and make sure you did that correctly on the microscopic scale. But we don't have to worry about any of that. We know exactly what happens when you couple a gauge field to a band in the Churn number. That's exactly what we worked out for the integer quantum Hall effect. And then later on, when we talked about Churn numbers, when you couple the external electromagnetic field to the electrons in a band with a Churn number, what we got was the Chern-Simons term, whose coefficient was the Churn number of the band. So exactly the same thing should happen here. So I integrate out, since the fermions have a gap, I can remove them and get an effective theory for the gauge boson. Now it's a strongly fluctuating gauge boson. It's an emergent gauge field, not an internal gauge field. And for each occupied Churn band, I will get coefficient 1. Okay, but now comes the key difference. The coefficient, this is not 1, but 2. And that's, and from our chapter on Chern-Simons gauge theory, we already know that's going to make a huge difference. That's M. So this whole thing is M equals 2. And of course, N equals 1. It's one Chern-Simons gauge field. Where's the 2 come from? The 2 comes from the fact that there are 2 spins. You have spin up and spin down fermions occupying the lower band. So each one of them gives you one Chern-Simons term with a unit coefficient, and they together give you a factor of 2. Okay, so there we have it. There's our first microscopic derivation of a Chern-Simons gauge theory with a non-trivial coefficient, M equals 2. And so now when we look at the exchange of the spin-ons, initially we started out in mean field theory, the spin-ons we said were fermions. But now this theory is telling us, no, they're not actually fermions. If you take 2 spin-ons above the gap and you move them slowly around each other, in addition to the Fermi factor that you already have, because they're fermions, you're going to get an additional statistical angle, which is pi by 2. If you go back and look at our expressions for the statistical angle. So these are called semions because they're halfway between a boson and a fermion. The statistical angle of a boson is 0, for a fermion is pi. And so therefore, this is pi by 2 or minus pi by 2, depending on which way you go. So these are semions, and they all have the same statistical angle, the particles, and that's what the spin-ons are. Now, if you take 2 semions and put them together, you get a boson. So that's the only non-trivial excitation here. It's the these semions. Yeah, okay. Sorry, 2 semions should give you back a fermion.
No, boson.
I know they do, but but the actual quasi-particles here themselves are fermions, right? So how do you get back an actual? Right. No, this is a right. Sorry, this is a model of bosons. This is a theory of spins. It's a theory of bosons because the spin is just a Bose operator. Yeah. So this is a topological phase which can only appear in a theory of bosons, and here the boson are the spins operators. They are physical spin operator. Right. That's right. Thank you.
U1 level 2 Chern-Simons is a bosonic TQ of T. But if you
Yes.
want to add
Thank
a
you.
fermion, you can times U1 level 1, additional U1 level 1.
Yeah.
But here you are.
Yeah. Thank you. That's right. No, so two semions make a boson, make a spin flip operator, because two Fs make a spin flip operator that we see already from from this decomposition. From here, if you have two Fs, then you get a spin operator. The spin operator is a boson. It's this capital B boson. So this is a theory of a bosonic fractionalized state where the quasi-particles are semions. So the semions are the spinons are neither bosons nor fermions, but the semions. Okay, this is never. I mean, this particular state I don't think has ever been seen in any experiment, but there have been a number of numerical studies of spin model which now show it. And let's see, what the future brings. I think the prospects are pretty good in the next, well, maybe in my lifetime. Okay. Questions? All right. So now, I could just say, okay, I'm done. I just now open up the chapter on Chern-Simons gauge theories and figure out the edge states, figure out everything, figure out the degeneracy in a torus and all of that. All those answers now apply. All I have to put is m equals 2 in everything we learned. But just for clarity, I'm going to try to proceed a bit further, not knowing all the things we learned about edge states. So let's try to do this, try to understand the edge states of this theory on a microscopic basis. Okay. So you remember when we did the edge state theory, we had to make some postulate we pulled out of our hat saying this is the only way to make the thing gauge invariant, and therefore that must be the answer. We don't like such arguments. We want to actually just work out what happens on the edge of this sample. So suppose I had a sample with this band structure, what's going on at the edge? Okay. So let's just take a very naive point of view and try to figure this out. So you have a band, occupied band. I'm only showing the unoccupied band, but there's an occupied band with a Chern number. And for now, let's even ignore the gauge fluctuations. So what we know from the chapter on integer quantum Hall effect, where we explicitly showed that every band with a Chern number had an edge state. So there must be, and that edge state was just an ordinary fermion. Okay. So there must be an edge state here for the occupied Chern band. But the important point is that there are two occupied Chern bands, one with spin up and one with spin down. So each of them will give their own edge state. So that's what's going to happen then. I have these Chern bands. Okay, so this is the sample. This is the direction Y, if I call it. And this is the energy. And I just have some occupied band in the center. Well, it's so these are the occupied states. And then I have an edge state there on this edge and that edge. And this happens for both spin up and spin down. So these are just free fermion edge states right now. I'm just doing the mean field theory. So what is the theory of the edge? Well, I already know that. It's exactly this chiral boson with m equals 1. So I have a upspin chiral boson and I have a downspin chiral boson. Okay. All right. But now how about the gauge fluctuations? So, this can't be the full theory because we know in the bulk that wasn't the theory. What about gauge fluctuations? Well, what do the gauge fields? So we have this internal gauge field which couples in the bulk to the fermion to the fermion current, right? So the gauge field is coupling, as you can see here, but this is really much more general. This coupling here is just A mu, J mu. And it just kind of follows from gauge invariance. That should be the coupling. It's A mu times J mu. So therefore, there should be a coupling even on the edge, which couples A mu to the current of the fermions. Right? Okay, so that's just again by gauge invariance. So we had fermions on the edge. You must have a coupling A mu, J mu. But what is the current on the edge? Well, the current on the edge, what we had learned was that the an epsilon mu nu missing here. I maybe miss. Yeah, we learned that the density was dx phi. Oops. Yeah. Dx phi over 2 pi, and the current up to a sign was d tau phi over 2 pi. So therefore, and this, so the Lorentz invariant current then is so J mu. I should write it out clearly. 1 second. Right. So on the boundary, we've learned from the bosonization formula that the density of a chiral boson is del x phi over 2 pi. The current is d tau phi. I'm sloppy about factors of I and -1, 2 pi. And therefore, the current J mu is, okay, maybe there's a minus sign here. It's really epsilon mu nu del nu phi over 2 pi. That's the current on the boundary. And that couples to A mu times J mu. That's the Lagrangian is A mu times J mu by gauge invariance. So therefore, yeah, I didn't write this correctly here. There's a typo. It should be an epsilon mu nu factor here. I will fix that in the online missing, but it doesn't make much of a difference. All right, so now, and I have this gauge field that's fluctuating. So and it couples to the total current, right? So the constraint, so this, the origin of this term is just the basic constraint on microscopically. Where did it go? Yeah, microscopically we have the constraint. We have the constraint that f dagger alpha, f alpha equals 1. It's not, the total density of fermions is not allowed to fluctuate. It's the sum on alpha on every site is 1. So what this tells us on the edge, when we integrate over the gauge fields, so when we integrate dA times e to the I A mu J mu over 2 pi, that's just a delta function. That's going to give us a delta function. And the delta function tells us that d mu sum on alpha, again, sum on spins, sum on alpha d mu phi alpha is 0. Meaning that there's no fluctuation in the total charge density. And that's exactly what it should be, because that's the constraint. The total number of fermions is not allowed to fluctuate. You're only allowed to make fermions from up to down. And quite remarkably, on this edge theory, this constraint is very easy to impose exactly. You just put this delta function. So this tells us that you just have a delta function and say phi up plus phi down is a constant. So the constant doesn't matter. So you make that equal to 0. So that means phi up is minus phi down, which is phi. And now you plug this in here, and you get your edge theory. And you get the edge theory with the famous factor of 2. So now this was, hopefully makes you happier about all the tricks that we introduced in the Chern-Simons gauge chapter, where we just used gauge invariance to fix the edge. But now here we're, just doing the path integral of the fermions in the bulk, including the gauge field. And we go to the boundary and you integrate or put in the constraint on the gauge field, that gives you then the factor of 2. So there it is. So that's, of course, we could have just got this answer from the previous chapter, but now I have a different derivation where I don't make any assumptions on some strange boundary conditions like a tau equals 0 that we used last time. Okay. Yeah, so I kind of really like this argument because it's one of the few cases where, this complicated constraint, which we only treat approximately in all of these theories, we're able to treat exactly. And it gives you in a very simple manner, just ties the two chiral bosons to each other. And it's, it's this very strong interaction that's ultimately responsible then for this factor of 2. And that's why this theory is completely different. But it's still Gaussian, but it gives you rather more remarkable properties, including the semionic statistics. Okay, so now, of course, we know the quasi-particle operators in the bulk that were just fermions. And we already know that the fermions are just e to the I phi in the bosonization language. And therefore, the spin-on becomes plus or minus I phi on the boundary. And the spin flip operator, like I said, gives you e to the 2I phi, because if one is phi up and the other is phi down, they have opposite signs, and you get 2I phi. Another interesting operator to consider is the spin density, not the total density, but the difference in density of the fermions. Well, that's this difference, including that factor of 1/2, and that gives you a 1/2 pi, gradient of phi. Okay, so now there might be one thing that's kind of bothering you, perhaps. The underlying system we started with had an SU2 symmetry and of spin rotations. But when we did the bosonization of the boundary theory, we broke that SU2 symmetry. We treated spin up and spin down with two separate chiral bosons. So in fact, we no longer have the SU2 symmetry in this theory. But if things were right, you should find that the physical operators like S plus and S plus and SZ, so this is SZ, should have the same correlation functions. But they look very different. One is e to the 2I phi, and one is 1/2 pi grad x phi. Now, it turns out if you work out the 2-point correlation functions of this, I guess this should have been another homework problem, but I've given you too many. They both give you exactly the same answer. So this theory here, this chiral boson theory, which looks like a U1, it has a U1 global symmetry. So this is the U1 Kac-Moody algebra at level 2. Secretly, it has an SU2 symmetry. And that SU2 symmetry is associated with these operators, e to the 2I phi and 1/2 pi grad x phi having the same correlation function. So in fact, even though you broke the SU2 symmetry in bosonizing the theory, in the end, you can recover it. Now, there's another way to do all of this using an approach that maintains SU2 symmetry at all times. That involves an SU2 gauge field in the bulk and non-abelian bosonization on the boundary. That's also a very powerful technique, which is useful in other cases. But here, we can actually get all the answers we need just by using abelian bosonization.
Is this related to the level rank duality?
Level rank duality. No, I don't think so. This is just if you take the C equals 1 theory at certain points, at certain radii of the C equals 1 theory, there's extra symmetries. If you just, if you look up Ginsburg's lectures on conformal field theory, then you find that central chart C equals 1 has many different CFTs, and at some points there, even though the explicit symmetry is only U1, the correlators all have, and all the operator spectrum has an SU2 symmetry. Yeah, I don't think level rank duality is a more complicated thing for non-abelian engaged theories. Maybe it's connected, I don't know. Maybe you can derive it in some way, but not that I know of. Okay. Other questions? Okay, so now, let's move on. We can do the next chapter. We have all this powerful technology. Let's apply finally then the famous fractional quantum Hall states. Let's apply this. Let's use this approach to get some understanding of the fractional quantum Hall states, which are, of course, the topological states that are best studied experimentally. Okay. So just to review, you get the fractional quantum Hall effect. Here, let's just take Landau levels. So we consider electrons of some density rho in 2 dimensions in a very large magnetic field. So you get a bunch of Landau level in a magnetic field B. And each Landau level, the density of electrons you can accommodate is B over phi naught. So that's the fully filled Landau level, but the density equals B over phi naught, where phi naught is the filling fraction. Phi naught is the flux quantum, excuse me. So if the Landau level is partially filled, then you get filling fraction, which is defined by the ratio of the density of electrons to the magnetic field. And the remarkable experimental observation, which was experimentally and theoretically complete surprise, was that at certain, what was first observed, for example, at nu equals 1/3, you had a gapped state with a Hall conductivity that was 1/3 of E squared over H. So sigma xy was 1 nu times E squared over H, when nu is the filling fraction of 1/3. And this was a plateau, and led to a lot of remarkable developments. So the first theory of this came from Laughlin, where he proposed a trial wave function, which explained a lot of things. And from that trial wave function, people, understood the connection to Chern-Simons gauge theories and many, many other things. And you can, starting from that wave function, you can derive a lot. Now that's, described in so many books and review articles that which I imagine you can read. So I'm not going to take the historical development. I'm just going to describe this by the approach we've been using, which is the parton construction. And from the parton construction, you can even write down and deduce Laughlin's wave function. But more powerfully, you can deduce the edge states theory, the bulk theory, the fractional statistics. Everything comes out very naturally in a way very similar to what we just did for the Carl spin liquid. So what's the basic idea? So the basic idea of the partons is to split the particle up, in this case the electron, which is the physical particle, into parts. And it turns out that for the Laughlin state, and also for the Jane states, as we'll see, at least the main sequence of Jane states, the division we're going to make is not split it into 2, which is what we've done so far, but into 3. So we take our electron and split it into 3 partons. Okay, so if I draw a picture, just to make this pictorial here. So you have your sample, and in the sample, you have some particles. So here are particles sitting in your sample. So here's your electron. And you are filling 1/3. So there are 3 flux quanta for each particle. So I'm going to clump them up just to make a picture. This is the physical magnetic field. So for each electron, there are 3 flux quanta coming in because you have nu equals 1/3. So what I'm going to say is that the electron is actually made up of 3 particles, psi1, psi2, psi3. And we're going to imagine that these flux quanta each act on one of the partons. So you have 1 flux quantum for each parton. So that's, very crudely the picture. Of course, we're going to do an actual calculation, so don't be alarmed by this very simplistic, kindergarten type drawings. So roughly speaking, you have 1 flux line for each electron, each parton now. And if you have a parton, which is also a fermion here to begin with, which has 1 flux quantum per parton, but it's going to fully fill its Landau level. So the partons will fully occupy 1 single Landau level. Okay, so that's the idea. So you have the electron, C of R. The operator splits into 3 partons, psi1 of R, psi2 of R, psi3 of R. Okay, so these partons have their own wave function and they all occupy a Landau level. So what is the wave function of the electrons? R1 through Rn. There's too many psi's. Let's make this capital Psi. This is the actual wave function. Well, that's going to be a product of the wave function of each of the partons. So parton wave function are called psi p. And we want the coordinates of the electron and the parton to be the same. So there'll be coordinates, R1 through Rn. Now, so each one of these is the parton wave function for a parton in a fully filled Landau level. Now, you may remember I told you what the wave function of a fully filled Landau level was. It was product on I less than j, and I'll ignore the exponential factors, which all work out correctly, times zi minus zj. This was the wave function times some exponential, which I won't worry about. Wave function of a fully filled Landau level, the van der Waals determinant. But I have 3 partons with the same wave function, a fully filled Landau level, and all of them have the same coordinate, so I'll just get this cubed. And that's the famous Laughlin wave function. Now, amazingly, you can also do this for other states. In fact, almost all the states that are observed, the so-called Jane states. And the way you do it is by taking one of the partons and have it occupy more than 1 Landau level. So imagine, suppose you have a situation where the 3rd parton is only half a flux quantum coming in for the 3rd parton. Well, if it has only half a flux quantum, that means it can fully occupy 2 Landau levels. And if you do that, you end up getting the 2/5 state. And in fact, that works very beautifully. So ridiculous as this construction sounds, it's the one that works in practice, remarkably well in so many different experiments. Okay, so that's all we're going to do. Here's a little bit more. Now let's do this more formally. So we take our electron and we split it into 3 partons. Okay, now we are gauge theorists, so we want to derive, every time we do a decomposition, there's a gauge field that got to come about. So now the moment I do this, I have now a redundancy. And I have 2 redundancies, one redundancy here and one redundancy here. In fact, if you're really being strict, there's really an SU3 redundancy and there's an SU3 gauge field, but it turns out you don't need it. So we'll just talk about the U1 gauge redundancy here, just to make our life simple. Okay, so therefore, there's a U1 gauge transformation generated by rho 1, where psi 1 and psi 3 have opposite signs, and another one, so I choose to make psi 3 special, where psi 2 and psi 3 have opposite signs. So it's a U1 cross U1. There are 2 U1 gauge fields. Well, that's sounding promising. We know we already had Chern-Simons theory with n gauge fields, so maybe we're going to get 2. In fact, you don't get 2 in the end because of the constraint. But anyway, so there seem to be 2 U1 gauge fields here, at least for now. So if you write down any theory of the partons, I'm going to have 2 gauge fields because there are 2 constraints. Okay. So that's point number 1. So now I take my original theory for the electron, which experiences a magnetic field due to the external gauge field. And then I write down a theory for psi 1, psi 2, psi 3, which experience not only the external gauge field, but also the internal gauge field. So now I look for a saddle point. Now, because I already have a magnetic field in the external gauge field, it seems reasonable that I will also have a magnetic field due to the internal gauge fields. So really, for each parton, I should be looking at the sum of the magnetic fields, the one due to the external field and the one due to the internal field. Okay. Now, first of all, you can see already from here, if there's an internal gauge field on psi 1, internal magnetic field on psi 1, the internal field on psi 3 is equal and opposite. If there's an internal field on psi 2, the internal field on psi 3 is equal and opposite. So these internal magnetic fields are not going to change the sum of the gauge field. So let's assume that there's some total magnetic field, BP, that each parton experiences. This BP involves both the external field and the internal field. So we have a constraint that the total field must be the sum of the internal fields on the 3 partons, because the internal fields always act equally and opposite on any pair of particles. All right. So now we have to choose B1, B2, B3. And it's really up to us to choose it. And how do we want to choose it? But we want to choose it in a way that the mean field has a gap. That's a good mean field. If you do a mean field theory, and then you get a state that's non-degenerate and has a gap, well, that means you can make progress from it. So you want to choose a field so that the mean field has a gap. And so basically, you always want to choose B1, B2, and B3 so that each parton occupies an integer number of Daniell levels, because only then the parton would have a gap in its spectrum. Okay. So if I do this more generally, right. So what can we say then? Let's do it over here. So we have, let's do it over here. No, let me make another page. Sorry. Let me make another page. So we have the filling fraction of the original electron is the density of electrons divided by B. So I'll just drop the factors of phi naught. They just are very common, and they just make a life very complicated. So filling fraction of the electrons is B. Then we also have B equals B1 plus B2 plus B3. Then what do we want? We want, now we also know that the density of the electrons is equal to the density of the partons. They're all equal, because every time you put an electron, you put one parton of each type. Okay, so that's something else you know. And then you want the partons to have occupy an integer number of Landau levels. So that what we also want is N1 is rho, because rho and rho are over B1. You want N2 is rho over B2, and you want N3 is rho over B3, with N1, N2, N3 integers. Okay, so now you have a set of relations. You give me a new, and then you try to find N1, N2, and N3 so that this all works. So this won't work for any value of nu. If you try to eliminate all the variables in these equations, only certain values of nu will this whole thing work. And if it works, then you're guaranteed to have a gap above the observed states, above the mean field theory. And the remarkable fact, which is I was stepping forward to that, is that essentially all observed states can be described by some choice of N1, N2, N3. And that's the beauty of it. In fact, they can also be, some of the N2 and N3 can even be negative. So the magnetic field can be pointing the other direction for some of the particles. So the simplest case is N1 equals 2 equals N3 equals 1. And if you just were to do the numerology of these equations, you'll find that that means nu equals 1/3. So that's the famous Laughlin case. So each parton sees exactly one flux quantum, and I already showed you that gives you the Laughlin wave function. So yeah, so B1 over 5, yeah. This is the case where you have exactly one integer Landau level filled, and nu is 1/3. The other important case is when two of them are 1 and the third is some other integer. So case 2, so this is the Laughlin case. And the other case is Jane, and I'm just taking the simplest Jane and Laughlin cases. That turns out to be N1 equals 1, N2 equals 1, N3 equals N. And then if you work out the numerology, you'll find the filling fraction is nu is N over 2N plus 1. And in fact, I remember this when I was at Yale in those days, and Jane was a postdoc there. And there were all these experiments going out showing this sequence of fractions, which just happened to be N over 2N plus 1. And there was this very elaborate theory of hierarchy, which famous people were talking about, which giving all kinds of fractions, but these particular fractions were nothing special in the original hierarchy formulation. And then Jane came up with this argument, which is pretty much the argument I've just presented, which gave this beautiful answer, smack on to what's being observed. So you can see with the benefit of hindsight, this is one of the triumphs of the parton approach, where the basic idea is you pick your partons carefully and then try to find a mean field that has a gap. And then there's a pretty good bet you're onto something. Okay, so that's what we're doing. We take our partons, we find a gap in the mean field, then we look at the gauge fluctuations. All right, so those are the Jane states, and you can write down the wave function. Then you have a wave function which has this factor of zi minus zj squared from the first two partons, and then the wave function of the particles in the higher Landau levels from the third parton. This is no longer analytic, So it's not really a wave function the lowest Landau level, even though the filling is less than 1. And this was, of some concern. I mean, I think that's the reason why other people didn't dare to write this down, because there was this dogma that whatever wave function you write down must be analytic. But it turned out that dogma was not correct. It's okay to have a little bit of analyticity, and in fact, the way Jane fixed it in numerical studies, you just drop the non-analytic terms, you just project them out, and then everything works. And project them out is similar to doing the gauge integrals, gauge fluctuations, and so this is the modern understanding would be, yes, you can project the gauge, project out the non-analytic terms. That's like doing the theory of gauge fluctuations, and that's fine because there's a gap, and the gauge fluctuations are all under control. So the key thing is really to find a mean field with a gap, and that's more important than forcing this analyticity. Anyway, that's my 2 cents worth. Okay. Right. So there it is. And now that we have this part-on construction, just like we did in the last chapter, we can work out the Chern-Simons gauge theory, figure out the statistics, figure out the edge states. It's really a matter of turning the crank now. But in fact, the way I'm going to do it in this chapter is the opposite of what I did in the previous chapter. We're going to do the edge states first, because it just turns out to be a bit simpler. Because on the edge states, as I showed you already, you can just do the integral over the gauge fields exactly. And there was just this very simple result that phi up was minus phi down. And we'll get very similar things here. So this way you can get the full K matrix. It turns out that this integer n is the same as the integer n in the Chern-Simons gauge theories. The number of gauge fields are left over after you have done all the projections. So that's why I called it capital N. So n equals 1 is the Laughlin case. So that for the Jane states, like n equals 2, which gives you the 2/5 fraction, is an example of the n equals 2 case, where there will be 2 independent edge modes and so on. Okay, I think that's 4 o'clock, so I will stop there. And then we'll finish the Jane states theory next time, and then I want to start really, in some ways, the most spectacular of the fractionalized states, which is the non-abelian Ising state of Kitaev. And again, I'll do it by this very general part-on type approach. We'll see that it just comes from a very subtle twist on the Z2 spin liquid is how you get the non-abelian states. I'm still learning up part of the non-abelian state myself, so I have the weekend to get everything right. But I think I certainly have understood enough to give the lecture on Friday. All right, any questions?
Yeah, I actually have a question. It sounded like we originally motivated having 3 partons by this nu equals 1/3 case.
Yeah,
but
yes.
Now that we see other cases, like why exactly was 3 the one that we picked, or why is 3 the one that works?
Yeah, you can pick others. So if you wanted to describe the fractional quantum Hall state at nu equals 1/5, then you will have to pick 5 partons and do it that way. I mean, it's just more work. I'm just doing the simplest case.
I see.
And then and there's the Jane sequences. There's more than one Jane sequence. This is the simplest of the Jane sequences that I'm describing here. So there's various other fractions that you get by putting one of those partons in a higher Landau levels, the others in the lower ones, and so on. I'm not an expert on this, but there's an incredible zoo of possibilities here. I'm just showing you the 2 simplest ones.
I see.
But as far as I know, every known state can be can be described by this parton constructions, including the non-abelian state. That's quite a bit more complicated, but yeah, that I won't describe.
I guess a follow-up, I don't know if this is something that you would readily have the answer to, but are there some states that can be equally well described with different numbers of partons?
It could be, but I'm not aware of. I mean, in the end, what's the invariant property of the state, which is not up for debate, is the total number of independent edge states. What are the edge states and what are the K matrix on the edge states? I mean, the K matrix can take different forms. You can take linear combinations and get other K matrices. But there's some equivalence class of K matrices, and that's not something you're allowed to change. So you want to have at least enough partons to give you the K matrix of the right rank. Yeah. And any more you add probably are unneeded, and you get rid of them by the constraints on the boundary. As you see, you can, that's why the edge approach is often the simplest thing to do, because you can put in all the constraints exactly and then get whatever the theory is. Yeah.
I see. Thank you.
Sure. Okay, great. So again, there's a review session, discussion session tomorrow morning, and see you on Friday for more fun with the Chern-Simons Gates theories.